But if we look at Vz on element 2, which is equal to 2487 Newton. Okay. So what we have is our shear stress is equal to 2487. Now this is a bigger value. Okay, so it's 11.717 times 10 to the power minus 6. I'm sure I've just calculated the coefficient, stupid me. 358.908 times 10 to the power minus 9. And then it's 52 times 10 to the power minus 3. Okay. So this will make up to be 2487 times 11.717 power minus 6 divided by 358.908 power minus 9 divided by 52 power minus 3. Is equal to 1.561 megapascal. And then we are going to look at the torque. The torque in the x direction given, or we have calculated, is 596.831. Okay. So this is 596.831 Newton meter. So the shear stress is equal to TR over J, 596.831. Right, 596. Let me check again, 596.831. The radius is equal to 26 times 10 to the power minus 3. Divide by TR over J, the second polar moment of area, 717.816. 717.816 times 10 to the power minus 6. So 596.831 times by 26 power minus 3 divided by 717.816 power minus 6 is equal to 21.617 or 618 megapascal. So the shear is also the same due to the torque, right? Because they are all on the surfaces. So this is also 596.831. The shear stress is equal to 21.618 megapascal. So if we look at a ratio, right? So if we calculate 0.585 divided by 21.618, okay, so 0.581 divided by 21.618. This is only 2.7%. Okay. So for element 1, we can see the force in the shear stress induced by the shear force is relatively small compared to the torque, right? You can see that, right? But the other one, okay, if we take 1.561 divide by 21.618, okay, then we multiply by 100, see how significant it is. Okay, 5.561 divided by 21.618 times by 100. This is 7.22%. And you say, Eugene, you know what? This is quite significant, right? The first one is 2.7. Yeah, 2.7 is kind of low, okay? But 1.561 relative to 21.618 is 7.22. Okay? Yes. Oh, Vz, I just take the shear force value. Yeah, if I were to draw, it will go down and then go up again, it'll be smaller value, right? Yeah, but I'm going to just take it for 24.87 now because of the reaction. Okay, I'm just going to get it based on the reaction. Right, so you can see like, whoa, this is kind of what? This is kind of huge, right? So 7.22 is kind of big, okay? But how significant it is relative to the maximum stress, the principal stress, okay? So now we are going to determine, we are going to focus on element 2, okay? We're going to focus on element 2. So element 2, if we look at element 2, now, due to My, right, the stress is equal to 0. Okay, so now we are going to look at element 2. I'll write down here to let you know that we are doing element 2. Okay, element 2. So for element 2, right, due to My, the stress X is equal to what? 0. Right? Now, then due to Mz, which is equal to 372.8, right, the stress in the X is equal to 372.8 multiplied by 26 times by 10 to the power minus 3, and then divide by the second moment of area, which is 358.908 times 10 to the power minus 9. So this will be equal to 372.8 times 26, 372.8 times 26 power minus 3 divided by 358.908 power minus 9 is equal to 27 times 10 to the power 6 Pascal. Okay. So from here, right, so if I were to just briefly sketch our element, right, we know that we have, it can be either a tensile compression, okay, so it's 27 times 10 to the power 6 Pascal. Let me see the tensile compression. So over here, element 2 is tensile, okay, and then we have a shear. Now the shear has two possibilities. One of the shear is just 21. We calculated one value to be what? 21.618. Okay, one of the shear is 21.618 times 10 to the power 6 Pascal. And then the other one will be what? The other one will be equal to 21.618 plus by 1.561. So this is due to the torque. This is due to the shear force. Okay. So we are going to compare if we include the shear force, okay, or the stresses induced by the shear force. So this is one shear force value. The other one, we ignore the shear force. Okay. So from here, we can calculate our stress average, which is equal to 27 times 10 to the power 6 divided by 2 is equal to 13.5 times 10 to the power 6 Pascal. Okay. And then when we look at our tau max, right, the normal stress will be the same for both. The tau max will be equal to 13.5 times 10 to the power 6 squared plus by 21.618 times 10 to the power 6 squared. Or, okay, we can include 13.5 times 10 to the power 6 squared plus by 23.179 times 10 to the power 6 squared. So this one is torque plus by the shear force. This one only has the torque. Okay. So this is 21.618 squared plus by 13.5 squared square root is equal to 25.487. Whereas the other one, 13.5 squared plus by 23.179 squared, 26.823 or 824 times 10 to the power 6 Pascal. So now when we calculate the stress max is equal to 13.5 times 10 to the power 6 plus by 25.487 times 10 to the power 6. So 13.5 plus by 25.487. This is equal to 38.987 times 10 to the power 6 Pascal. And the other one will be equal to 13.5 times 10 to the power 6 plus by 26.824 times 10 to the power 6. Okay, so 13.5 power 6. So it's equal to 40.324 times 10 to the power 6 Pascal. So if we're going to calculate the average difference between the two, so will be equal to 40.324 minus by 38.987 divided by 2 over 40.324 plus by 38.987 divided by 2 times by 100. So this will be equal to 40.324 minus 38.987 divided by 2 divide by 40.324. Wait. 40.324 minus 38.987 divided by 2. So the denominator is 39.656. 40.324 plus 38.987. 40.324 plus 2. Yep, 40.324 minus 38.987 divided by 2. 40.324. My calculator is not behaving, or is the user. 0.6685 times by 100. Okay, so 0.6685 divided by 39.656 times by 100. The difference is 1.685%. Okay. Or if you want to look at the difference in magnitude, not as a percentage. Okay. So the difference is equal to 40.324 minus by 38.987. 40.324 minus 38.987. 1.337 megapascal difference. Okay. Relative to the maximum is 38.987 without the what? Without the maximum, without the shear force. Okay. So it's very small. You can see it's small. So that's why we can ignore it. Okay, due to the maximum. So if you were to ignore the shearing force, you just need to put a what? Factor of safety. When you design your shaft to be safe, okay, have a factor of safety of, in general, is about 1.2. Okay, for design work, we tend to use 1.2. Okay, the 1.2, you will learn this in 305. The 1.2 will include materials impurities, inhomogeneous of the material, and shear stress like this that we have ignored. Okay. Okay, now I'm at peace now. Okay, I mean, this as I said, this is the first time I'm doing this in detail. Okay, I always take it for granted from the textbook that it can be ignored, but I did not check. Okay, so this is as I said, this is the first time I'm checking it. I'm not checked before. I trust the textbook, but I think we should check. Yeah, I think it's a good exercise. Okay, so the next topic that I'm going to teach that will be included in your exam, or not just included in the exam, it's part of the topic that has to be included, is use U criteria. The U criteria for ductile material. Okay, And the emphasis over here is this is only suitable for ductile material. Okay, we cannot use for brittle material. And I'll highlight to you what do we mean by brittle and what do we mean by ductile. Okay, so for ductile material, there are two. Okay, there are two general types of U criteria. But before we go anywhere, what do we mean by ductile material? Okay. Right? How do we know it's ductile or not? Okay, so I'll list down a few materials that are ductile over here in general. So ductile material, okay,